And please volunteer to pick some songs for our sort of pre-game show music, because otherwise there may be more Weird Al in your future. I guess there's in a Weird Al kind of mood today, I guess. Anyway, yes, revealing my misspent youth. Okay, so any questions about last time or anything else before we start? Okay. You know what? I'll have to actually watch one of these videos to see how those awkward pauses come off on video. All right, let's just get going then. Um, so where do we leave off? So last time we were talking about multiple roots and the derivative. Remember the derivative of an arbitrary polynomial is the derivative of a polynomial with coefficients in an arbitrary field is defined just totally calculus one style. You just you to take the derivative of a monomial, you move the exponent down front and you subtract one from the exponent. Just totally formally defined. Anyway, so the point is, so for that somehow through some miraculous accident of fate, actually still satisfies the product rule, and so as a result, for any polynomial little f with coefficients in big F, that polynomial has multiple roots in some field extension of big F, if and only if the GCD of f and f prime is not equal to 1. That is, if f and f prime are not relatively prime. Okay, and so in particular, the sort of useful special case of this is that an irreducible polynomial has multiple roots in some extension of, I guess maybe the best way to put this, in some extension of f exactly when f prime is equal to 0. So as a corollary, if the characteristic of f equals 0, geez, I'm not sure. I'm not sure we've mentioned characteristic in here or in some other course. So let me, just in case anybody finds that to be a strange looking kind of word, let me sort of remind you what the characteristic of a field, or actually of a ring is. It's the order of, so if you have a ring with unity, the order, I think we've mentioned this very briefly when we first talked about rings over here, but just to remind you, the characteristic of a field F, or more generally of a ring R, is the additive order of the element 1 in that ring. So it's the number of times that you add 1 to itself to get 0. Unless the order is equal to infinity, in which case we define the characteristic of f to be 0. So right, so I mean, and the two examples to keep in mind are that so the rationals have characteristic 0, and the characteristic of z mod p is p. So those are sort of the two basic examples that you want to keep in mind for the characteristic of a field. Though we will actually see other examples of fields of characteristic p just in momentarily. Anyway, so if the characteristic of a field capital F is 0, then in any irreducible little f with coefficients in big F has no multiple roots in any extension of f. So that's because, well, there's no way that you can get the derivative of some function. Sorry, not some function of some polynomial to be equal to 0 when your characteristic is 0. I mean, unless that polynomial is constant. So I mean, you know that from calculus. It's just that Yeah, I guess I should do an example of, so just as another aside, so example, if, say, the characteristic of f equals 2, and f of x, say, equals x to the 4th plus 1, then f prime equals 0, right? So, and the reason is because when you well, I'll even go a little further than x plus x squared plus 1, x to the 4th plus x squared plus 1. Yeah, so it's just for the sort of silliest reasons that if all the exponents in your polynomial are even, and when you pull them down in front, they turn into zeros because the characteristic of f is 2, and then you get f prime equals 0. Okay, so that was a little bit messy, but it's life. So are there any questions about the theorem that an irreducible f has multiple roots in some extension of capital F exactly when f prime equals 0, and the corollary that that you never get multiple roots of an irreducible when you have characteristic when your field is characteristic 0. Are there any questions about what the theorem and the corollary say before I take a minute and prove the theorem? Okay. So, right. So proof of the theorem. And it's a really pretty short proof. If f in f bracket x is irreducible, then the GCD of f and any other polynomial equals f if f divides g and 1 otherwise. The only way that f can divide the polynomial f prime of strictly lower degree, possibly degree negative infinity, is when f prime equals 0. Right. So again, so yeah, the only way you can get multiple roots is if right. So the only way you can get multiple roots again is if the GCD of f and f prime is not equal to 1. Well, the only way then that you can get the GCD of f and any other polynomial not equal to 1 is exactly in the case where the GCD where f divides that other polynomial, and the only way that f can divide f prime is because f prime has lower degree is when f prime equals 0. Well, something like that. Anyway, the proof of that isn't so important, especially now that I've sort of done it. Like, well, that wasn't so important. But the important thing is that when you the thing that we'll actually, we'll actually use both of these, the theorem momentarily. But the really important thing that we'll use all the time in chapter 16, it's one of those technical results that we'll use in chapter 16, is that in characteristic 0, you never get multiple roots of an irreducible. So does that make sense? That last bit, that when in characteristic 0, an irreducible can never have multiple roots? Say yes in the chat, or ask a question. Why? Okay, so Ravi says, ask why. How far back do you want to rewind? Okay, so you buy the theorem. So Ravi's asking, saying, so you buy the theorem. That's so the theorem seems okay. All right, and you're asking. So let me say proof of the corollary. Yeah. So what's going on there with the corollary? Proof of corollary. When the characteristic of f equals 0, no positive integer is equal to 0. Right. So having characteristic 0 is equivalent to saying that no positive you never have a positive integer equal to 0. So f prime of x, which is going to look something like n times a sub n x to the n minus 1. So actually, let me go back to pen instead of LaTeX, just in case LaTeX isn't such necessarily the most. So when f prime of x, remember, it looks like this: n times a sub n x to the n minus 1 plus n minus 1 times a sub n minus 1 x to the n minus 2. Right. So this is, so when you take f prime, again, yeah. So when you take f prime, you're really just doing it like Calc 1 style. You bring down the exponent, and you subtract 1 from, then you subtract 1 from the exponent, and do the same thing over here. So that can never be equal to 0, assuming that a sub n, that you haven't written out your polynomial in some silly way. Assuming that a sub n is not equal to 0, this is never equal to 0 unless f is a constant. Unless f of x is a constant polynomial. So right. So basically, what this is saying is that when the characteristic of capital F is 0, then this condition that you need in order to get multiple roots, that f prime is equal to 0, that condition never happens. That's all it is. So Ravi, does that make sense? Let me show the. Well, no, I actually don't need full page. Let me sort of scroll up so you can. Oh no, I guess I need full page here. Oops. There we go. So let's just look at all those pieces at the same time. The theorem said that an irreducible f has multiple roots exactly when its derivative is equal to 0, and the corollary says that if the characteristic of f is 0, which means you never get this circumstance where actually let me f of x equals 4x cubed plus 2x equals 0. Right. So in characters, so the way that you get a polynomial to have a derivative equal to 0, well, this isn't irreducible, but basically the way that you get a polynomial to have derivative equal to 0 is when all the coefficients are when all the exponents occurring in the monomials of that polynomial are all divisible by p. So like, so here, if you have characteristic 2, that's when all the coefficients are have even all the monomials have even degree, and so in characteristic 0, when you bring those exponents down, they never turn into 0. Okay, so you think that, so they never turn into zeros. So let's see. I think in the theorem, the corollary. Where did we prove the other part? Oh, well, oh, I see. So, yeah, well, okay, that's a good question. Let me add that in. Oh no. There we go. So let me add that in. Sort of conversely, if f prime equals 0, then the GCD of f and f prime equals f, which is not 1. So there, that's the, oops. So that's the converse direction. Does that make sense? Ravi, does that make sense? Okay, still processing. Right, so in the first half here, so in the, let's see if this works. In the first half here, no, that didn't work at all. All right, in the first half here, we showed that that if you have multiple roots, then you must have f prime equals 0. And over here, we show that f prime equals 0. Then the GCD of f and f prime is f, because the GCD of f anything in 0 is that first thing. Oops. So, Ravi, does that make sense? Okay, yeah. Okay, so any other questions? Yeah, I remember encountering this derivative thing the first time. It kind of blew my mind that you just did it algebraically and actually meant algebraically and actually meant something. Madness, but there it is. Anyway, so yeah, and so remember the important thing is the corollary in characteristic 0. Irreducibles never have multiple roots. All right, so now we turn to finite fields. Oh no, and a slide I forgot to finish. Oops, fail. Okay, well, let me just start typing. So the first facts about finite fields is that because, let's see, because finite fields are finite, and so the goal of what we're doing here, goal is to understand, at least to some extent, all finite fields. So we're going to kind of classify all finite fields. The first thing to note is that because a finite field is finite, they must have finite characteristic, right? The additive order of 1 must be finite. Characteristic. Let's see. So let's see if I can remember this. So the second thing, you can tell I'm just sort of getting a little tired here because I forgot to finish this slide. Oh well, sorry y'all. Yeah, because finite fields are finite, they must have finite characteristic. If the characteristic, okay, so yeah, so let's just, I think this is sort of standard in the rest of our discussion. So let's make K be our standard name for a finite field. If the characteristic of K equals A times B is composite, then K can't be a field because A and B are then 0 divisors. So the characteristic of any finite field has to be prime for some integer primes. It's just because we've spent so much time recently talking about other strange primes. The characteristic of P must be some prime for some integer prime. Let's see. What else do we need to know? That means that there is a copy. There exists a copy of FP inside K because what you have inside K somewhere is a copy of the integers mod P, right? And so it's equal to Z mod P as a subfield of for some P, where P is equal to the characteristic of K inside as a subfield of K. Right. So every finite field has inside it a copy of Z mod P, and which is therefore the field, really the field FP. All right. That also means that K is a vector space. So remember, I'll say is a field extension of FP, which means that K is a vector space over FP, which means and the order of K is a power of P. We'll usually call this. It's actually not unhelpful to have a standard notation for this. So we'll usually call this the order of K. So we'll usually denote this. Denote this K equals the order of K is Q, which is going to be P to the R. So that'll be. So we talk about those numbers K, Q, and P and P to the R so often. That's sort of helpful to have those that standard notation. And I think that's all. I think that's, yeah. So sorry, I just kind of did that off the top of my head because I forgot to write it. I forgot to put it in the slide last night. But I hope that wasn't too fast. So again, let me go. I'll just say it all again. So because a finite field is finite, it has to have finite characteristic, right? Because you can't have an element of infinite order of a finite additive group. If you had a ring of composite characteristic, and so the characteristic K is A times B, where both A and B are greater than 1, then K can't be a field because A and B are therefore zero divisors, which means because B times A added to itself B times will be equal to 0. Oh no, sorry, A times B will be equal to 0. My bad. And so the characteristic of K will be equal to P for some integer prime P. That means that somewhere buried inside any finite field is a copy of the integers mod P where P is a characteristic K. Which also means that K is a vector space over FP, which means that the order of K is a power of P. So just using sort of the theory that we've developed so far in terms of fields in general, we now know the very useful fact that the order of K, the order of any finite field, is a power of a prime. So yeah, so the characteristic is P, and the order of that finite field has to be a power of a prime. So is everybody good with that so far? Hi, Carlos.
Hey, how's it going?
Hey, how's it going? You missed the Weird Al, but maybe that's just as well. That was our playing music today. Okay. So that anyway, yeah. So if everybody else wants a little time to cogitate on this, well, you can do that as we move on to the next thing. Let's move on to an example. So yeah, I think this is an example sort of mentioned in the book, and it's a good example. So let me just sort of do it again. So the point is, yeah, what is the point? So what do I want to do here? So what I want to do is I want to just sort of construct one example of a finite field that's not Z mod P. And I think I've actually done this before, but it's worth doing again. I think I actually maybe constructed F8, but still. So example. So let K be. So I want to take F2. So the field of order 2. So I want to take polynomials coefficients in the field of order 2, and I want to mod out by x squared plus x plus 1. As you all know from the homework and various other sources, x squared plus x plus 1 is irreducible over f2. So it must be the case that so it's irreducible over f2. So k is a field. So remember, when you when you take a ring of polynomials and you kill an irreducible polynomial, you get a field. So now so let oops, and now I should segue back to handwriting. Let me go back to handwriting here, or whatever. So let alpha be the image of the polynomial x, the term x itself in K. So it's like the coset. It's like the coset x plus I, if you like, where I is the ideal generated by x squared plus x plus 1. Oh, in K. There we go. In that case, we see that from before, recall from results we've mentioned a couple times, but are worth repeating again, because the degree of our irreducible is 2, the dimension 1 alpha is a basis for K over F2. Right. So in other words, K is all the F2 linear combinations of 1 and alpha. So that's 0, 1, alpha, and alpha plus 1. So K has 4 elements. The order of K is 4, which is 2 squared. So this is sort of P equals 2 and R equals 2. So this is, well, let me write that out actually. So yeah, it's a little, I probably should have done 8, but that's fine. This is P equals 2 and R equals 2. So let's see. So note that the characteristic of K equals 2 and not 4. So K is not Z mod 4. So one error that everybody makes, I actually made this error until quite late in the game. What does this do? Oh, that's what that's how I get that. Okay. All right. So one error that I used to make until quite late in the game, until probably after like 5 to 10 years after getting my PhD, is that I always used to confuse Z mod 4 with the field of order 4, but it ain't so, because this means that that 2 equals that. So what happens here is that it's still always true that 2 is equal to 0 in K. It's not that and not sort of 4 equals 0, something like that. So let's see, and what else is useful to do? I think it'll be useful to write out a kind of a very small multiplication table. Oops, I don't want to do that. I want to write out a multiplication table of the non-zero elements of F4. So one of these, so some of this is not so interesting, right? So the row and column corresponding to 1 are not that interesting. So let me. So the interesting part here is sort of when you try to fill in this stuff over here. Yeah, okay, that'll actually, which will actually illustrate a couple things. Okay, so let me scroll back here. So oh yeah, something I forgot to mention up here is that because alpha is the image of x in k, and k is defined by killing x squared plus x plus 1, that means that alpha squared, oops, let me erase that. Oh no, undo. I need a little eraser. So I guess that first symbol is the total like eraser of death, and that I want to. Oh no, I really meant to erase that, buddy. Come on, erase. It does not want me to erase that 2. Never mind. Wow, that's weird. Okay, there, 2. Alpha squared plus alpha plus 1 equals 0. Yeah, so that's true. So alpha squared plus alpha 1 equals 0. And so when you see that, so I think I did this before in class, but let me do it again. So when you actually compute with a finite field, the thing you want to do, or actually any field defined by killing some polynomial, one of the things that's very helpful to do is you rewrite that defining relation in the term. The highest term is equal to all the other stuff put at the other side. Of course, here 2 equals 0. So when I have not made a sign error, because in characteristic 2 you cannot make a sign errors. When I have the alpha on the left-hand side and I move it over to the right-hand side, it's still plus alpha, because plus alpha is equal to minus alpha. Anyway, the point is that alpha squared is equal to alpha plus 1. And so alpha times alpha is equal to alpha plus 1 over here. So does that make sense, what I wrote, where I got that alpha plus 1? Good. And now here's another. So I'll do another one on the side over here. Now alpha times alpha plus 1 is alpha squared plus alpha. So that's alpha times alpha plus 1. And so that's equal to alpha, weird, alpha plus 1 plus alpha. Because again, anyway, we're always applying this rule, alpha squared is alpha plus 1. But 2 alpha, right, so, well, you tell me, everybody type in the chat window, what does that simplify to? Yes, right, that's equal to 2 alpha plus 1, which is 1, because 2 is still equal to 0. So you get a 1 over here and here. Ooh, here's a fun thing. And now we have a most amusing thing that's actually becomes important in a minute. When we have alpha plus 1 quantity squared, that's equal to alpha squared plus 2 alpha plus 1 equals, but 2 alpha is 0, so you get alpha squared plus 1. So this is the joke that people always make is this is the freshman dream, that finally the square of the sum is actually the sum of the squares. So that's sort of worth noting as an exclamation point. Whoa, alpha plus 1 quantity squared is in fact finally equal to alpha squared plus 1 squared, and that's actually a general kind of phenomenon that will become important later. Anyway, so when you replace that alpha squared with an alpha plus 1, that cancels out that you have alpha plus 2, and so alpha plus 2 is in fact alpha. And so does anybody recognize this here group? This is actually one of the problems. Oh no, I don't want to do that. That's just gonna make a mess. Anybody recognize this group? This multiplicative group here? You want to type that in the chat window, or just open up your mic and sort of say, what is this group isomorphic to? That was jarring. We suddenly went back to group theory, huh? Okay, so let's try this. So somebody want to type in the chat window. So this you can see this is closed under multiple. This is the set 1 alpha plus 1 is closed under multiplication. It is in fact the multiplicative group of the finite field K, and so, gosh, that's terrible. Let's see if I can get this to erase again. That looked so promising before. There we go. All right, so the non-zero. Remember, the non-zero elements of a field form a multiplicative group, and so since this is a field of order 4, the multiplicative group has order. Everybody type it in the chat window. Count of 3. 1, 2, 3. Type. Okay, good. Yeah, so that's right. It has 3 elements: 1 alpha and alpha plus 1. And so, what is the isomorphism type of that group of order 3 is? Well, you put it in a symbol or type out the words. Somebody want to give it a shot? So the multiplicative group of K is isomorphic to? Yeah, Z mod 3. That's right. It's or actually, let me call it something funny notation. It's a little confusing to call it Z mod 3, though. That is correct. It's isomorphic to as so the multiplicative group K times is isomorphic to the additive group Z mod 3. But let me actually call it C3, the cyclic group of order 3. And let me introduce that notation here. Cyclic of order 3. All right, so let me see if I can move this around a little. And there we go. Yeah, so the multiplicative group of K is cyclic of order 3. Well, I mean, because any group of order, you may vaguely remember, any group of order 3 is cyclic of order 3. Oh, we have to remember groups pretty soon, folks, in chapter 16. So, we'll ease back into that. So that's not so surprising. Any group of order 3 has to be cyclic. But what is much more surprising is that every finite field has a multiplicative group that is cyclic. A remarkable fact. Okay, so yeah, I think this is. Let's see if I can do that. All right. So, are there any questions about? So, are there any questions about this example F4 before we go on to sort of the general facts about finite fields? Everybody ready to move on? Or ask a question if you like. Okay. So let me go back to this view. Okay, so here are 5 facts about finite fields. It's really actually 6 facts, but I can't resist the alliteration. So here's 5 facts about finite fields. So let P be a prime, let Q be P to the R, our standard notation, and let K be capital K be a field of order Q. So the facts in order of proof. This is slightly different from the order presented in Artin, but this is sort of the order in which we will prove these things. So the first thing is that the elements of capital K are roots of x to q minus x. Yeah, so capital K is a field of order Q. The multiplicative group, so it will follow then that the multiplicative group of K is cyclic of order Q minus 1. I mean, you know it's order Q minus 1 because the multiplicative group is the non-zero elements, so you just throw out zeros. There's Q minus 1 things in it, but the remarkable thing is that group is always cyclic. That's a wacky fact that I really can't, still really haven't quite wrapped my mind around after all these years. So 3 is sort of the classification thing. I mean, I guess this is, you could put this in terms of two facts, and will in fact take 2 proofs. But you know, in order to preserve the alliteration, keep it down to 5 facts. It's with this is one thing. There's a unique. There exists. I guess let me write this out as a sort of one sentence slogan, or one statement slogan. There exists a unique field of order Q equals P to the R. And so people talk about the field of order Q because all such fields are isomorphic. Okay, so going back to our, so that's the third thing that's true. Let's see. The fourth thing is that if you have the field of order Q, so instead of saying a field of order Q, we're really thinking the field of order Q. K contains a subfield of order P to the K exactly when K divides R. And the fifth fact is that the irreducible. This is really a pretty cool thing. The irreducible factors of x to the q minus x over Fp, the field of order P, are exactly the irreducibles in Fp bracket x whose degrees divide R. Wow. So yeah, so somehow when you factor this one polynomial x to the q minus x, it contains both everything. It contains everything about the field of order Q. Within that one polynomial, you see everything about the field of order Q and all of its subfields. Pretty cool. This is like I should have looked this up. Who invented the theory of finite fields? Hey, I've always wanted to do this. I always have students Google things, so let me Google something here. Who invented the theory of finite fields? It is, Galois, of course it was Galois. There we go. I can't believe I forgot that. Yes. So thanks to Galois who worked all this stuff out. That's right. That's right. So that's right, because that's why these things are often called Galois fields, because their theory was pioneered by Galois. Interesting fella. Anyway, so good stuff. All right. Are there any questions so far about what these 5 facts about finite fields say before we go? And I think, we're going to take the rest of our remaining half an hour before spring break, such as it is, to go through the proofs of those facts, because the proofs are just cool. So again, everybody ready to move on? Okay, maybe some of you are reserving judgment, but that's fair enough. Okay, but we will come back to these 5 facts about finite fields many times. Okay, so here's so the first fact is that the elements of K are exactly, or precisely. I should say, be a little more precise here. Exactly, the roots are. Here's a little more precise statement here. Are precisely the roots of x to the q minus x. So that is in other words, each element of K is a root of x to the q minus x, and all the roots of x to the q minus x to the q minus x splits completely over K. Okay, so let K be a field of order Q, and we observe. So here's a proof of fact number 1. So let K be a field of order Q, as we always say, and we observe that the order of the multiplicative group is equal to Q minus 1. So by Lagrange's theorem, I went there. Yeah, so somehow this is the part of the course this is the part of or part of your year in graduate algebra where it all comes together. Where at some point we sort of blend together all the stuff that you did last semester about groups and finite groups and whatnot, and yeah, right. And it comes together with the ring and field theory that we're developing this semester. Anyway, so by Lagrange's theorem, the multiplicative order of any a in k times a little space here divides q minus 1. And actually, let me and I'm going to write in that superscript up here. There we go. K. So so if you have any multiplicative element of the multiplicative group of our finite field K, the multiplicative order of that element, you must divide q minus 1. In other words, a to the q minus 1 equals 1. Or in other words, a to the q minus 1 minus 1 minus 1 equals 0. So any non-zero a in K is a root of x to the q minus 1 minus 1 equals 0 equals 1. And since 0 is a root of x, well, is the root of x of the polynomial x, all elements of K are roots of x times x to the q minus 1 minus 1, which is equal to, as promised, x to the q minus x. Conversely, and here's an important point to remember. So remember, this is something that you know is true in like high school algebra, especially those of you teaching college algebra right now. So from like high school algebra or college algebra, you remember that a polynomial of degree 7 has at most 7 distinct roots. But remember, we actually showed that follows from sort of more general stuff. And so a polynomial of degree q, since the degree of x to q minus x is q, x to the q minus x can have at most q roots. So K contains all of the roots of x to the q minus all of the, and therefore distinct roots of x to the q minus x. And we can write, actually, I don't think I put this in the statement, but it actually follows from this proof. We can actually write x to the q. This is a lovely formula. X to the q minus x is actually the product of all terms x minus alpha, where alpha is in K. Neat, huh? I just think that's a really cool. I think that's a really cool formula. So the polynomial x to the q minus x factors into the linear factor of the. It's exactly the product of so given any finite field K of order Q, the polynomial x to the q minus x factors in K as the product of all possible linear factors x minus alpha. So are we good so far? I guess I just think that's cool. Whoa! That's not what I want to do. What happened? Yeah, this is what I want to do. Okay, I missed. There we go. Oops. I misnumbered that, but there we go. So Yeah. So and the punchline again is that the elements of K are precisely the roots of x to the q minus x. So we good so far? Okay. All right. Let's go back to proving these facts. All right. So now, yeah, I must have been a little tired last night. All right. Anyway, so the next point is that this is not fact number 1, but fact number 2. My bad. Okay. So fact number 2 is is that we want to show that the multiplicative group of our finite field K is cyclic. Oops, there's a little bit of explanation that I have to sort of shoehorn in here, but that didn't work. Okay. All right. And oh yeah, right. I always like slavishly follow the book, but this is actually slightly different from the proof in the book, and it may be a little bit simplified. It's something I'm working on for my other class. When I write that textbook, it's going to have this proof in it. All right, here's a sort of explanation as to why the multiplicative group of a finite field must be cyclic. So first of all, the relevant definition here is I want to define the exponent of a finite multiplicative group. So the exponent of a finite multiplicative group, capital G, is the smallest little n, a positive little n. So I guess we want to have little n greater than 0. It's the smallest n greater than 0 such that x to the n equals 1 for all elements x of G. So for non-abelian G, this is actually kind of maybe a sort of, it's like for any G, it's the least common multiple of all orders. So I guess that's worth mentioning. This is actually the least common multiple of all orders of elements that appear in little g. And so let me fix that there. So yeah, it's the least common multiple of all orders appearing of elements in G. And so there we go. All right, and in general, that has some. So if you have an element of exponent 60 or something, if you have a group of exponent 60, there's not necessarily going to be an element of order 60 in that group, but it's a corollary. It follows from the classification of finite abelian groups, for example, that the exponent of a finite abelian group, like K, the multiplicative group of our field K, so that's a finite abelian group. So it follows from the classification of finite abelian groups, for example. You can prove it other ways, but the classification certainly does it. That if you have a finite abelian group of exponent n, there exists an element of order n. So the point of all that is that we want to show that the exponent of K multiplicative, which I'll fix in a minute, is equal to Q minus 1. So I guess it's not that we want to show that. It's enough to show that the exponent of K is equal to Q minus 1. Sorry, of K multiplicative. Okay, hang on a second. I have to close the door so I'm not yelling up to my family doing their stuff upstairs. 1 second. All right, sorry, I'm back. I can now yell to my heart's content. And I love yelling. All right, so it's enough to show that the exponent of the the exponent of the multiplicative group of K is equal to Q minus 1. So now, so we're going to do that by contradiction. Yeah, so we're going to proceed by contradiction. So now we're going to suppose that the element, the exponent of K, of the multiplicative group of K is some number n, strictly less than Q minus 1. So in that case, by the previous, by the argument from the proof of 0.1, we see that every non-zero element of K is a root of x to the n minus 1. And therefore, by the same argument, every element of K, each of the Q distinct elements of the entire field K is a root of x to the n plus 1 minus x. But, and here's the catch, I think that this is just the cutest proof. Here's the catch. But n plus 1 is strictly less than q. Right? The assumption is that the sort of our contradiction hypothesis was that n is strictly less than q minus 1, so which means that n plus 1 is strictly less than q, which means that the polynomial x to the n plus 1 minus x has more than n plus 1 roots. Contradiction, and we're done. I love that proof. I mean, most of it is from Artin, but yeah, I put my own little spin on it. Yay! Yeah, so let's look at that whole proof again. Yeah, so again, we want to show that that the multiplicative group of K is cyclic, and so by group theory, by your first semester, by the classification of finite abelian groups, the thing we want to show is that the exponent of the multiplicative group of K is equal to Q minus 1. Well, suppose it's smaller. Then this argument, then the same argument from the proof of 1 shows that you have a polynomial of degree strictly less than q, which has more roots than its degree. Contradiction. So is everybody good with that? Say yes in the chat box, or questions. Questions, or say yes in the chat box. How do I get the last line? So Rabbi asks, how do I get the last line? What part of the last line? Maybe if you want to just unmute yourself and conclusion about the n plus 1 roots. Oh yeah. You get the last part because each of those q elements, it's because each of the q distinct elements of K is a root of x to the n minus 1 minus x. Yeah, let me do that. Let's see. Is this actually going to work? Yeah, it has more than n plus 1 roots, the q distinct elements of capital K. So does that make sense where you got the more than n plus 1 roots? Okay. Any other questions? Good question, Robbie. Thank you. Okay. All right. So now we've checked off. Let's see. not the first facts. Where's the, oh, here, 5 facts. So we've checked off that the elements of K are precisely the roots of this magic polynomial x to the q minus x, and that K is a cyclic, that the multiplicative group of a finite field is cyclic. And now we get onto sort of the most important one. Actually, if you run out of time for the other ones, it's not a big deal. So let's get into the most important one, that there exists a unique field, a unique finite field of order Q. So here goes this. Right. So the first thing is that suppose we're going to construct this field by we know that this is always possible. So where does this come from? So first I want to construct a field of order Q. So recall, oops, let me sort of blow this up again. So recall, you can always add roots to split anything. So if you have, that is, if you have any polynomial, you can always sort of construct an extension field to split any polynomial. You can always add on all the roots of that polynomial and make a finite extension and get a finite extension, which is therefore still a finite field. There's my little thingamabob. Yeah, so construct a finite extension capital L of f in which the polynomial x, the magic polynomial x to the q minus x splits completely, and let K be the set of all roots of x to the q minus x and L. So we claim that K is a subfield of L, and so oh, right. Oops, I forgot to do something here, but okay, but fortunately I remember how to do it. Okay, so the first thing is that we first claim that K is a subfield of L. So it's enough. So it's enough to show that K is closed under addition, negation, product, and inverse, and it contains 1. So the sort of oddly enough, the interesting parts of that are showing that K, which is, remember, K again is going to be, or K is the set of all roots of x to the q minus x. It's all the set of all things such as x to the q is equal to x. And we want to show that if alpha and beta are roots of x to the q minus x, and then so is alpha plus beta. Well, here's the remarkable thing that happens. If you have, when you look at alpha plus beta raised to the power p, this is just another very cool thing. So if you write out the binomial theorem for that, you get alpha to the p plus p choose 1, alpha to the p minus 1 beta, and then there's just a bunch of things over here that all involve chooses. P choose something, and then you have p choose p minus 1 times alpha beta to the p minus 1 plus beta to the p. Oops, not beta squared, but beta to the p. Oh, there's my cursor. Okay. So yeah, so that final term there is beta to the p. There we go. Okay, so and the remarkable thing about that is that all these terms, all these p choose k's, where k is strictly between 0 and p, are all divisible by p. Actually, but I don't want to say that. Well, I guess I should say they're divisible by p. Just because, oops, and they're just for silly reasons. Like if you write out if you not for particularly deep reasons, if you write out the formula for binomial coefficients, there's a p in the numerator that can't possibly be canceled out by anything in the denominator because k is strictly less between 0 and p, and therefore doesn't have any p's in it. So this is divisible by p, so it is equal to 0 mod p. And remember, even though the order of our finite field k is q, remember q equals p to the r. So even though the order of our finite field is a power of p, we're still working in characteristic p, so p is equal to 0. So the point being is all these terms in the middle drop out, and so we're left with alpha to the p plus beta to the p. Remarkable. So this this is sort of, I mean, what's sort of really remarkable about this, if you go on and if you study finite field, and there's a lot more. We're just going to do like one class worth of finite fields, but there's a lot more you can study about finite fields. This is actually so the pth power. The point of this is actually a field automorphism. Is what you end up showing, called the Frobenius automorphism. Yeah. So what this is sort of the interesting step about that of showing that the pth powers give you an automorphism. Anyway, so in any case, going back to qth powers, if I take alpha plus beta to the q, that's equal to alpha plus beta to the pth power, and then you do that r times. But each time you apply the pth power, you do this weird automorphism thing, and so this is equal to alpha to the p to the r plus beta equals beta to the p to the r, which is equal to alpha to the q plus beta to the q, which is equal to alpha plus beta, because alpha and beta are in K. So alpha plus beta is in K, because remember the defining characteristic of an element of elements being in K is that their qth powers are equal to themselves, and lo and behold, the qth power of alpha plus beta is equal to itself. Right, and there's something I want to do here. Insert another page here. Oops, 4 minutes left. Oops, I don't want to do that. I want to insert a page here. Okay. All right. So so let me say that the proof that minus alpha is in K is similar, but maybe less complicated. Well, and actually, there's two cases. P is 2 and P equals odd. So I'll leave that to you. That's sort of presented in the book. All right. So now so K is a subfield field of L. Are there Q elements in it? And actually, let me switch to typing here because I think it'll be a little bit faster. So now the question is, so remember, K is a subfield of L. It's the set of roots of this polynomial x to the q minus x. Well, so K will have Q elements in it unless x to the Q minus x has multiple roots. Right, so remember, yeah, so this is actually, we're about to use the multiple root thing again. So K will have Q elements in it unless let me call that f of x equals x to the Q minus x has multiple roots. But f prime of x is equal to Q, x to the Q minus 1. This is just the derivative, minus 1, which is equal to minus 1 because Q equals 0 mod P. So the GCD of f and f prime is equal to 1. So f does not have multiple roots. So the roots of f are distinct, and K contains exactly Q elements. Yay! Okay. Yeah, I don't want to try to rush through this. Yeah. Let's see. So, yes, I'm happy with this. Yay! So I think next time I will, after break, such as it is, we'll do uniqueness. I think it's a useful and fun argument. How we obtain the uniqueness of finite fields, and then I think the other stuff is sort of less important and less part of the main thrust of the course. So then I think we'll do that, and then we'll just sort of go on to chapter 16. So all right. So but let me ask you. So if you can turn, if you're up for it, for being a little bit recorded, can you turn your mics on? So are there any questions about due dates, about our exam 2, which will be a take-home exam, about how lax I'm going to be about problem sets in general? Are there any questions? Oh yeah. So exam 2. So Ravi asks, what homework is exam 2 on? So I mean, it's open book, so this is in some ways a little less important. But exam 2 is on PS 04 through 07. I said at the beginning, but let me repeat it. And the chapter and the parts of, or rather, the parts of problem sets 4 and 7 that have to do with chapters 12 and 13. Problem set 7 has a couple problems from chapter 15, but that will not be on exam 2. Any other questions? You can just, if you just say, just type no in the chat box, or just open up your mic and ask questions, or no questions. Okay, so so if you have further questions, feel free to email me, and I might be reaching out and trying to contact you. I still want somebody to try to DJ, pick a song, a play-in song for after break. I'm determined to have you each do this at least one time, and not have me just pick all my strange songs. Anyway, so everybody take care, stay safe, until we speak again. And I might, and feel free to poke me over spring break. I'm not going anywhere. I hope you're not going anywhere. I hope you don't have to move, for example. But anyway, so stay safe, stay at home, shelter in place. And this is a tough and weird and crazy and bizarre and terrible time, but we're all gonna get through it. So take care of yourselves and take care of each other. I mean, from far away, take care of each other, and I will talk to you over spring break, if not soon, after spring break, if not sooner. So bye, everybody.
having you.
Thank you.